So my talk is, as you see, mostly about really the beginning of linear algebra. So what you do the first couple of weeks in teaching the subject. And then, but at the end, I have something to say about the SPD and also a challenge about interpolation. So there's a little bit of unsolved stuff at the end. So just at the start, well, what do I do in the first day of a class? I talk about, with examples, with small examples, linear independence and dependence of the columns of a matrix. And I emphasize how to multiply a matrix by a vector, that it's a combination of the columns. Every student arrives knowing about dot products, and I try to say, see the big picture, combine the columns, and similarly for matrix multiplication, you're combining the columns of a matrix C with coefficients from R, and that's what I really want to tell you about. So, and because I'm aiming at a factorization, A equals C times R, where C tells us about the column space of the matrix and R about the row space of a matrix. So that just in those first weeks, you're seeing spaces and a bigger picture than just dot products. Okay, let me see if I can do this. Yeah, so here's an example. This will show everybody here, will see immediately what C and R are. So the matrix C has a full set of independent columns going left to right. So in this matrix, everybody sees that the third column is a combination of the first two. So the first two are the independent columns that go into C. And then R, have a look at R. R is the key matrix here. So the R begins with the identity matrix, where it just reproduces those independent columns. And then the important new part of R is the last column, the 2 and the 1. And of course, that's telling us what combination of the two independent columns, so 2 times the first column plus 1 times the second, gives the 3, 7, 6 column. So there couldn't be a simpler factorization. And I want to show you that it's, C is C is a full set of independent, a basis for the column space, we could say. And then R tells us how every column of A is a combination of the independent columns in C. So part of that is the identity, where we're just reproducing those independent columns. The other part is a combination. Okay. So is that all right for the start? That's the idea of C times R. So it's a really, you could say, trivial factorization. But I think at the beginning of the course, trivial isn't a bad thing. And what's more, we're learning how to multiply matrices. That's the first or the early understanding has to come. Okay. So you see that R has in this case the identity in the independent column part, and some F matrix in the rest. Yeah. So my idea is to actually understand, because this is a celebrated matrix, this matrix R. It's the row-reduced echelon form that poor students are forced to compute and compute and compute, and without telling them what it is. I mean, we're matrix people, so we should just express it as matrices. Okay, that's my sermon there. Okay, so and it becomes, the whole thing becomes sort of clear. That if you put the independent columns in C, then what is R? Well, where in the columns that you're just reproducing, then R is the identity. But in the other columns, in the dependent columns, So the dependent columns are combinations C times F of the independent columns. That's just so that the whole row-reduced echelon form has turned into a factorization instead of a fact. It's grown, I could make a pun and say it's grown from a fact to a factorization, and that's a lot better. Right. I never thought of that before, and I'll never repeat it. Yeah. Right. And let's just note that the independent columns might not all come first, so that you may need a permutation matrix on the right to shift the columns around to put them so we can think of the independent columns as coming first. So there is a factorization that uses a P, but it's clear that you need permutation. Okay. So A is CR. Are we okay on that? That's the factorization. And from just looking at it, those columns of C span the column space of R. They're a basis for the column space because they were independent. And now R is also a great matrix because from A equals CR, just matrix multiplication, the rows of R are giving you combinations coming from C now. We've looked at it from right to left. The combinations of the columns of C are giving the columns of A. And combinations of the rows of R are giving the rows of A. And out of that falls the first wonderful fact in matrix theory, so wonderful that the column space and row space have the same dimension, R. Okay, so I guess I feel this is the way to begin. Of course, for you, I'm going way faster than I would in a classroom. Okay. Oh, and then let's recognize, make the link to row reduction. What is the algorithm? Because that's what it's been up to now. Reduced row epsilon form has been seen as an algorithm that produces the identity matrix and some other stuff. And we're trying to say what that other stuff really is. Yeah. So you can think of this is, if I were to code it. So Cleve Moeller told me that MATLAB, he put in MATLAB an RREF program, and that nobody has used it for 50 years or something. But I just, here's a little bit of a column at a time instead of an entry at a time approach to it. I'd be happy to send a paper that you could take a few extra minutes to see that. And now, next, why do we want this? What use can we make of this row-reduced form? So, and the answer is, it tells us the null space of the matrix. That's what all those row operations did. It simplified the matrix from the original matrix A. Those row operations simplified it to R. R is the row-reduced echelon form. And so instead of solving AX equals 0, we solve RX equals 0 to find the null space. And that's, well, as you see, it's superbly easy to do. So here was an example. There's a matrix AX equals 0 on the left at the top. Then I did the row reduction to get Rx equals 0. And now in the middle lines there, you see the actual factorization. The first two columns of A were independent. The third column and the fourth column were dependent, and those numbers 3, 4, 5, 6 are the numbers that went into F. F told us what the combinations are that give the dependent columns. And then, of course, Now, to find the null space, we just solve Rx equals 0, and everybody can quickly solve Rx equals 0 with, well, the three equations are written at the top. 0 equals 0. I didn't quite say it exactly right. The matrix R is the result of reduced row echelon form with the 0 rows removed. So only the R, small r, rank non-zero rows remaining. And of course, we solve that equation and we find that those numbers 3, 4, 5, 6 appear with minus signs in the null space. So that's how I would, of course, I'm going at a very excessively fast here. But my main point is to show you that a factorization can do a lot more than an algorithm. Just to see it, you can understand more from a factorization. Okay, a little bit more about this, I think. Oh, yes. Oh, well, now, so now I'm looking at it as looking at the block matrix, and that makes it even easier to see what's going on. So we have the matrix A, and we would like an R by R invertible matrix up in the top left corner. Sooner or later, we have to exchange rows, exchange columns, and the point is then, so that's with P sub R and P sub C. So take any matrix A of rank R, then with a permutation of the rows and a permutation of the columns, we can make that matrix W in the corner, that upper left corner, that R by R upper left corner, full rank, invertible. And it's all we're doing in elimination is look at the step there on the top line from the original matrix with permutation to put the W in a good place. So we have W and then 3 other submatrices. And what has elimination done? It has multiplied that first row by W inverse, because we know we want to get the identity matrix. And it has subtracted a multiple of the first rows from the other rows because we know we want to get the 0 matrix there. So that is row reduction, elimination on a general matrix of rank R when an R by R submatrix, invertible submatrix has been moved into the upper left corner. So, yeah. And this is an interesting fact which may be well known, but I hadn't quite seen it, that if you have R independent rows of a matrix, which we have, and if we have R independent columns of a matrix, that if you look to where the rows meet the columns, that is an R by R matrix and it's invertible. So there's elimination in just the simplest form possible because the permutations were done first. I hope this is like you feel that, okay, this elementary thing is in a better form because it's in a matrix form. Okay.
Yeah, are you suggesting that we should throw out the echelon form entirely in the algebra courses and go to CR or CUR?
Oh, yeah. Oh, thanks for mentioning U. Yes. CUR. Yeah, of course, because it allows me to say that although everything in this talk is trivial, the inclusion of a matrix U, a sort of connecting matrix, mixing matrix U between the C and the R, Well, so in big randomized linear algebra, C is a randomized choice of columns, R is a randomized choice of rows, and U is the matrix that connects. Yes. Now, what was your question, Alan?
That was a good answer.
Oh, okay.
My question is, should we throw away echelon form from linear algebra courses and go via CR or maybe CR?
Yeah, I think so. I think the factorization CR is worth learning, and it must go back to, Aristotle or somebody, because it's really not deep, but it's just to learn the steps of row reduction without seeing the matrices is just wrong. Yeah. Well, okay. Here is my little comment about the SVD, and in parallel with the eigenvalue problem. So on the left we have the eigenvalue problem. On the right we have the singular value problem. So everybody thinks of, or I think a student naturally thinks of the eigenvalue problem as Sx equal lambda x. I'm taking S to be symmetric in the eigenvalue problem to make things parallel. So Sx equal lambda x is a simple way to remember what's the eigenvalue problem. Then, of course, we go on to state it as the spectral theorem and as a factorization of S into eigenvectors times eigenvalues times transpose, x lambda x transpose. Now I want to look at the SVD. So the SVD, I just want to do it in parallel. So we had Sx equal lambda x. What is the corresponding fact for singular values? It's AV equals sigma u. So the point is we have V and U are different vectors, but V is a set of orthogonal vectors in the row space, and U is a set of is an orthogonal basis in the column space. And those are orthonormal, so we need some constant sigma to catch up. So I guess what I'm trying to say is for a first understanding of the SVD, to quickly say to a student, A equal U sigma V transpose, that's too much to take in. We understand, oh yes, U is an orthogonal matrix, V is an orthogonal matrix. So we've understood the properties, but A equal U sigma V transpose is a kind of a mouthful, whereas AV equals sigma U tells you what the SVD has amazingly achieved. It's found orthogonal vectors that are taken to orthogonal vectors. That's really how I think of the SVD. To find orthogonal vectors, orthogonal inputs, where the outputs are also orthogonal. Again, you know this well, but I'm just saying that should not be lost by repeating U sigma V transpose. And let me attempt a proof, a sort of a new geometric proof, or maybe new, for 2 by 2. So the next slide is a proof of finding orthogonal inputs that give orthogonal outputs. Can I just show you this attempt at a proof? Okay, start on the left. We're looking for 2 orthogonal vectors so that when we multiply by A, the results are orthogonal. All right, let's try, first of all, V and W to be the coordinate vectors. So on the left, that is the left still up there. Yeah, okay. So V is the orthogonal vector 1, 0, and W is 0, 1. And when we multiply by A, we don't get orthogonal vectors. AV is somewhere, AW is somewhere, and then unless it's a very exceptional matrix, their angle is not 90 degrees, some angle theta. Okay, accept, we have to accept, we're still looking. So now try W and minus V. So try 0, 1 and minus 1, 0. Okay, so W still goes to the same AW, and minus V goes to minus the AV. And you see the point that the angle, which was theta in the first picture, is pi minus theta in the second picture. And so how are we going to finish this proof? By magic or continuity or whatever words we dig up, that somewhere in between that first pair and the second pair, where the angle was less than 90 and it became greater than 90, somewhere in between is a little v and a little w, so that AV is perpendicular to AW, so that the angle is 90 degrees. Again, I haven't seen this, but I'm sure it's been thought about before. But I bring it up first because it's something that in 2 dimensions, I mean, the SVD in 2 dimensions is really a really nice thing. You know, it's saying you start out with 4 entries in a matrix, 2 by 2 matrix. Start out with 4 entries. Yeah, do I say anything about that in the next slide? No, let me come back to okay, well, I'll say it in words and then continue with that last slide. So we have 4 entries in the matrix, and where are the 4 entries in the factors of the SVD? Well, in the first rotation, that's 1 angle. In the last rotation, that's 1 angle. And in the diagonal matrix sigma in the middle, that's 2 numbers. So those are the 4 numbers. Or maybe 2 by 2 is too obvious. So let's go to 3 by 3. So the original matrix has 9 numbers in it. And then the rotations. So how many parameters are there in a 3 by 3 rotation? Well, as every airline pilot knows, there are three ways to redirect its plane. So 3 angles in U, 3 angles in V, and 3 stretches in sigma. So altogether 9. I'm just counting parameters as a way to sort of reinforce the beautiful idea of the SVD to beautiful factorization. Of course, it's just the right thing. Okay, may I bring up one final subject before lunch? So this is not simple. As far as I know, it's not done. And so it's kind of a challenge. It's a challenge to create a better code than we have to do interpolation. That's a fundamental scientific problem. And AI, deep learning, has sort of solved that problem. I mean, that's one way to look at the achievement of DI, is that it gets a ton of training data, and it creates a function that pretty much interpolates the data in a stable way, so that if you have new data that's pretty close to the old data, you get an output that's pretty close. So we're looking for stable interpolation, and we all know that polynomials of high degree are disastrous. And but yet we didn't really know what to do, and one part of what comes up in deep learning is to do something nonlinear. So let me just remind you what deep learning's answer is. But deep learning is, or the big neural net, that code is written for, supercomputers. And I think there's a challenge to like, okay, keep the key idea, but shrink the code to a size that could solve ordinary scientific problems of interpolating data. So let me just recall what the big code does. Okay, sorry. Yeah, okay, so here's my summary of the function that's created by deep learning. I want to just point out some of the features that are important. Maybe the most important feature is that the way to create a complicated function is a chain of simple functions. So that's something that maybe didn't certainly, I would have thought if we had the complicated function, if we had a lot of data, we would create a complicated function, but I wouldn't have thought of making it a chain of simple functions. So we just have to look at those simple functions. What do they have? So they have weights that we're choosing, like the coefficients interpolation, we're choosing these weights. That's normal. And they have nonlinearity. That's the unexpected from the point of view of Lagrange interpolation or something, to have this nonlinear function ReLU appear applied to each component. So I think you probably ought to know this ReLU function that turned out after people started with much more complicated nonlinear functions, thinking smoothness was important, but actually piecewise linear was quite satisfactory and made the computations easier. So ReLU is this, sorry about that crazy name, is the function that's 0 and y. So the slopes are 0 and 1. So it has a discontinuous slope, but that doesn't matter. And then you have to, maybe the three steps that I think of as having been critical and having been recognized by the computer scientists and shown how to use it are, first of all, to have a chain of simple functions. Secondly, to have each of those simple functions just linear, so the coefficients are linear, but then to every component of every vector, this ReLU gets applied. Who would have thought of that? Yeah. And then finally, how do you compute the weights? So there are thousands or tens of thousands of weights. So you have a big optimization problem. So to get instead of fitting data by making some algebra work, we have a giant optimization problem that where W is the data that we would like to get, F is the function we're using, U is the input, and X is the set of matrix weights that go into all the components of the chain of functions. And that big optimization problem is usually solved by stochastic gradient descent. So there are ingredients there that Lagrange interpolation by polynomials never thought of, in nonlinearity, stochastic gradient descent, but it works. And I guess my thought is, the challenge part is, suppose you had a more, these problems are often solved with supercomputers for very, very many components, thousands, tens of thousands, hundreds of thousands of components. Suppose we just had a more straightforward problem of interpolation of a more moderate size. how would we do it? How would we use the ideas that have emerged through deep learning in writing a new code? I think it's a problem that deserves some attention. Well, thank you, and thanks, Alan, for being who he is. Thank you. So
Thank you, Gil. That was a beautiful proof of SVD. And I don't think I was quick enough on the draw to, were you explaining how to generalize that to more dimensions
no,
than
and
two?
I doubt that it can be done. It may be just.
I bet it can be done, but
well, it would take a better man than me to do it.
So anyway, thank you. That was beautiful.
It's really a 2D proof. The key point is that it emphasizes what the SVD is about, finding perpendicular vectors that go to perpendicular. Yeah, thanks.